Good afternoon. I promised you a proof of isotopic extension theorem. I'm going to postpone it either to the end of this lecture in case I get through what I want to get through in time, or till next time, because it's time to start talking about the Torres trick for an arbitrary handle and quoting Wall at the right moment, theorem of Wall. So we're going to have a diagram here again, just as before. And so it starts, as always. I can put the K ball in, K handle, make it a K handle or a zero handle. I mean, you should always think that the BK just sort of comes along for the ride and you can almost ignore it's there, because it doesn't really make any difference except at one crucial moment. So anyway, we have a map, an embedding of a K ball crossing, you know, whether it's Rn or the N ball, makes not too much difference because the interior of the N ball is Rn. So, but let's do this. And so we have an embedding into some PL manifold. So the manifold of dimension K plus N. So it has a piecewise linear structure. Think of smooth structure if you like, because lots of this works just as well. And we'll call this embedding H. And we should think of it as a K handle, being mapped in. So I want this to be piecewise linear in a neighborhood of the boundary. So the embedding is PL on a neighborhood of the boundary, which is the K minus 1 sphere across Rn. So it's always relative to that. So the motivation for doing this, for understanding handles in this way, what we would like to do is isotope this embedding, keeping it PL on the boundary, and have it make the whole thing PL. In other words, make it nice across the whole handle. Now suppose you could do this. So the motivation, the aim is, if you could do this, then you could put a piecewise linear structure on any manifold. Because what would you do? Well, you have two copies of R K plus N overlapping. So you want the overlap to be a PL homomorphism. Well, it's just a homomorphism to start with because we have a topological manifold. So you want it, but you want to make it PL. Well, just as the argument we did last time on the overlap, you can take this overlap and use a triangulation to divide it up into handles. So first of all, you see from the one chart coming down, it has a zero handle in it that gets embedded into this PL manifold. And both these are copies of Rn. They both have standard PL structures, but they don't overlap right. So take a zero handle from here inside of it, and it embeds. Well, then you want to wiggle that zero handle a little bit and make it PL. And you do that with all the zero handles, if you can. Well, then, if you can, then the zero handles are embedded. And now you take a one handle between two zero handles, and you try to make it embedded piecewise linearly. And you keep doing that with the one handles and then the two handles. And if you never run into a problem, then you've made the overlap piecewise linear, and you do that with all the other overlaps, and you've made a PL manifold.
So,
now,
slightly lost. I can see this is the inductive step. I've lost the aim, so that you've got the.
So the aim,
you want to construct a PL homomorphism.
I want to make this topological manifold piecewise linear. I want to put
fine
charts that overlap piecewise linear. And if you're more familiar with the smooth case, think that way. Because the same, except we know that we can't do it smoothly because Curvaire had a non-smoothable 10 manifold back in 1959, 60. You take Miller's exotic 7 sphere, which is made up of two 7 balls which are attached by an interesting diffeomorphism. And that's a different story. Never mind that example. But anyway, this idea of fixing things up handle by handle by handle enables you to do a lot of things. And so that's what you want to work on this.
How do you know that the topological manifold in the domain has a handle decomposition?
Well, because on the chart, remember I was taking a pair of charts. And the chart is a copy of Rn, so it has a handle body decomposition.
Yeah. But it's not quite the same as saying that every topological manifold has a handle decomposition.
That's right, it's not the same as
So
that.
what,
But I don't need to say that.
no, so what are you saying?
I don't need to have, so you see I have two charts and they overlap.
Yes.
Now, this chart is PL, has a PL structure,
Mhm.
standard rectilinear PL structure on Rn, K plus M. And so I have, from that PL structure, I get handles. I drew that yesterday, you know, we take the second barycentric subdivision and you, so on. So you have handles here, and now the handles are being embedded in this PL copy of Rn.
Mhm.
And now I want to just straighten, that's what we call it, straighten the handles one by one until the overlap is piecewise
But it's
linear.
not, that's fine, I just wanted to make
Yeah,
clear
yes.
to people that it's
Yeah.
not the same as assuming that the
That's
topological
right.
manifold has a
You
handle
don't
decomposition
have
all
to
by
do that.
itself.
You don't have to
Fine.
do that. So that's why we would like to, so the aim, let's put the aim down. If possible. Show that this embedding H is isotopic REL boundary. I don't want it, it's PL, already PL there, I don't want to mess that up. REL boundary to a PL embedding. Well, at least on BK cross the end. We just really want to get it along the core of the handle, along a compact core of the handle, that's good enough. So that's what we'd like to do. Okay, so same game, immerse the immersive torus, BK cross N, Tn, the Tn minus a point. And this is our fixed immersion, we call it alpha, it never changes. Now, the game's gonna be a little bit different here. We're gonna pull back this PL structure to a new PL structure here. So theta, we call it theta. Theta is the PL structure on BK cross Rn, induced by H. So theta is standard near the boundary, which is sk minus 1 across Rn. Because it's a PL map. So therefore, when you pull it back, you get the standard PL structure there. So pulling back a PL structure is it's like pulling back a smooth structure. You know, what is a structure? Well, it means that you have coordinate charts that overlap piecewise linearly. Well, so you take the coordinate charts here that overlap piecewise linearly, and if you pull them both charts back the same way by H, they still overlap piecewise linearly by definition, and that's the PL structure theta. That's, in a certain sense, is an easy thought, but I shouldn't tell stories of Dennis Sullivan, but I sent him a handwritten note in 1968 describing this, and he said he stopped reading when I said pull back the PL structure because he stopped reading. didn't care for it. Which is
Well,
partly why I ended up collaborating with Larry Siebenman, who I met later, instead of with Dennis, who I already knew. Anyway, that's, so we have this structure theta. Now this, remember, is always a nice embedding, so particular. That was always a PL embedding, or smooth embedding. It was a very nice embedding. And so that pulls PL structure, and then we'll pull back to one here. We'll call that one, I don't know, theta 1. So now this map is a PL. It was PL with the standard structures. Now it's PL because I pulled this structure back. So at this point, I've got a piecewise linear structure on a manifold, a non-compact manifold. In the end, the PL end of dk across Tn minus a point, theta 1. The PL end of this is a PL structure on an n plus k minus 1 sphere across R. Because this is an n, if you put the point back in, this is an n plus k manifold. Maybe I meant something different here. Maybe I should have said dk across n minus 1 across R. So I'll call that theta 1 just because it's a restriction, same name. So now we have to know, I need to know something or other, I need to know that PL structure is standard in order to fill it in. So I want to put the point back in, which means putting the K ball back in. So I want to put that back in, I want to extend the PL structure across it. Well, fortunately in 1968, that was a known fact.
It's no longer known.
Well, not by as many people as that. Because people were putting boundaries on non-compact manifolds. Browder did it first in the simply connected case, and then Sieberman did it in the non-simply connected case in his thesis. And so basically what you want to do is put a boundary on here, which looks like Sn minus dk across Sn minus 1. And you can do that, and then if you put that boundary on, then you can fill it in. So so we just quote, we can extend this PL structure, theta 1, to dk across Tn, and we'll call that theta 2. So we're going to just extend the structure. So this is based, this must be, I don't know, this is Browder, Sieberman. Various people were putting boundaries on things, and that's what's needed here. And just to embellish that point just a little bit more, I'm missing a point. So I've got a PL structure out here, and it gets smaller and smaller as I get closer and closer, and I want to fill it in. Well, if this outside non-compact manifold has an end, and then I can put a boundary on that end, and that means I can put a nice boundary on that end, and then I fill it in with a nice PL bowl. That's how the game goes. Okay, so I filled it in, so now this is sitting inside dk across Tn with a structure theta 2. By the way, all along, it's the same game as, this hasn't changed. All along, we have these maps. And these are what? These are just inclusions. So these are inclusions, and on the boundary they're what they should be, etc. Okay, now what I would like to have here is what we want. We want PL homeomorphism for L boundary to the standard BK cross TN. Just the, no exotics, no possibly strange structure, just the standard one. That's what we want to have. But it may not be there. In fact, what are the issues? Well, so the issues here are that the issues are a theorem of Wall, which I've already stated. So manifolds PL manifolds homotopy equivalent to BK cross TN, REL boundary, are classified by the third cohomology of BK cross TN, REL boundary, with Z2 coefficients. This is a wall. So this is a full, uses lots of non-simply connected surgery. I think maybe the last lecture I'll try to give you a sketch as to where that Z2 comes from, and just why that's there. Because it's Rocklin's there. It's really a four-dimensional effect. So there's that theorem, and so here we are. We have a homomorphism, not just a homotopy equivalence, but that doesn't really help. So this is possibly one of these exotic ones. There may not be a PL homomorphism across here. But something extra that's known is that it's known that if you take double covers of this torus, the Z2 thing can vanish. So there's kind of an obstruction sitting inside here, and you need to double cover all of the circle factors, just to be sure you wipe it out. So it's known that a large enough, well, that means doubling every circle, a large enough cover kills the invariant. They're classified with this, so this is a group, and it kills the elements in this third cohomology. Unless k equals 3. What's the problem with k equals 3? Well, there's this, you have a board. I'll say more about this another time, but if you've got one of these exotic guys, one of these PL manifolds, there'll be a boardism to the nice manifold, to the standard one. So there'll be a boardism there, and that's one higher dimensional. And inside there, somehow there's going to be the algebra is going to call for a 4-manifold of signature 8 that runs from one side to the other side of this boardism. And that 4-manifold of signature 8 doesn't exist. And that's why there's a Z2. But when k is 3, it may run between something, in a sense, 3-dimensional here and something 3-dimensional out here. And it runs between there, and then when you're taking double covers of the N torus, this is unaffected. So that's why you can't necessarily kill it when this is a 3-handle. I mean, if this is if it's a 4-handle, k is 4, then let's say, maybe it's easier to say if k is 2, then some of this Bordism has to slop over into a circle factor, and then it gets covered there. So anyway, this is an additional statement to Wall's theorem that we need. So, what do? We take an in-between step, and this is a 2 to the, n-fold cover, because every one of these circles is going to get double covered. And now we get a structure theta 3 that we cover. And although this PL homeomorphism might not exist here, it does exist here. So now we have a PL homeomorphism. Something, I don't want to call it H yet. Call it G. PL homeomorphism G, which is PL homeomorphism. You can read the identity on the boundary, because this was the standard PL structure in the boundary, and that Wall's theorem works for L boundary. So it's taken to be the identity in the boundary. Now we're finally in a position to use the torus as we had before, and observe that when you take the universal cover now, you've got a bounded homeomorphism. Always it's that boundedness that is a crucial fact. So now we take a further cover, e to the something exponential, to bk cross Rn. Call that H to bk cross Rn. And so this one is PL and is bounded. And therefore isotopic to the identity. Well, now we're using the fact that on this end ball, since it's a small end ball down here, and it's small, it sits inside sort of the zero handle, this end torus, and it's sort of small all the way up, and it's kind of never touched. It's never touched. So that's just what we had before. So the thing to observe is that capital H let's say it this way. Capital H is PL. So now run this backwards. If you run this backwards, you see that you've got a map just on this small BK cross BN, just on that part of it. You have a map where this is a homeomorphism, which is PL, so it's the inverse is PL. So you have a PL map. This is just a subset. And now you come back here and you got another PL map. So H inverse followed by little h is PL. So that's one observation. But then H, capital H inverse sub T is an isotopy from, well, this PL map from a PL homeomorphism to H. Because when HT is the identity, I haven't said which way T is going. 0 to 1. It's going between H and the identity, whichever way the time goes. So this thing is taking you from H inverse to the identity inverse. Identity. So this this isotopy will take you from a PL map to H. In particular, when you get to the identity, then on the unit ball, this is just BK cross BN, still BK cross BN, it's still BK cross BN. So it's really here, and you get H. So if you now think of your domain, and it's basically this or this, you're moving H to a PL embedding. So this is the isotopy. It's all rail boundary. That's all been preserved. Boundary's been preserved all the way through, and so right. So that's what we were looking for. The isotopy that moves this handle to a PL handle, and it works fine except in dimension 3. Use your walls there. I mean, this is all kind of elementary, but you do have to stick in this hard theorem of walls. So we can conclude from this well, what's one of the easier things to conclude? Just from this. So the Hauptvermutung. So Hauptvermutung said that if 2PL, there's a question or a conjecture, if 2PL manifolds are homeomorphic, then they are PL homeomorphic. So let me say a little about this, just for those. I mean, I haven't even defined PL for you. Maybe I did once. And you know what simplicial complexes are, and then a simplicial map always takes a simplex to a simplex. It might drop dimension. It might take a 2 simplex down to an edge. It could do that. But if it's a homeomorphism, it won't. So if you just think of a simplicial map, simplicial homeomorphism between two simplicial things, that's not so hard to understand. You would say that these two things are simplicially the same. Well, you might very well have to subdivide at times. So then we say that this map from this simplicial complex to this one is piecewise linear if, when you subdivide here and here, then it becomes a simplicial equivalence. So that's what a PL homeomorphism is. It's just from, you've got, you have to be manifolds, but let's think of manifolds. If this manifold is, you subdivide it so that it's a simplicial complex, and the same thing with this one, and then you say they're PL homeomorphic if you can subdivide perhaps more, subdivide perhaps more, and then there's an isomorphism taking simplices to simplices. That's what PL is. You've always got subdivisions in there. You're always allowed to subdivide further and then make it simplicial. Okay. So that's what this is saying. You have two PL manifolds. Well, there's a pair. After subdividing, there's simplicial complexes. And then to say that PL homeomorphic says there's a subdivide some more, and you get an isomorphism between simplices. Why was this in German is the main question? Is that the translation?
Well, the main problem. The main conjecture, actually.
Yeah, okay. So why was it given that name? Well, Poincaré had, and others had defined homology simplically. If you have a simplicial complex, then they did the simplicial homology. But then they were confronted with the problem, suppose that they had two spaces, two manifolds, or two spaces, but two manifolds that were homeomorphic. but they were subdivided in different ways, would you get the same answer? Well, they weren't sure. That's why they asked this question. If they were subdivided in different ways, if you had two PL manifolds which are homeomorphic, you compute their homology groups for each, you'd like to know that you got the same answer. And you would get the same answer if this were true. So that's why they asked the question, back in the 1910s or something. Well, of course, as soon as they came up with singular homology, that was, the 30s, I guess, that was proved. That singular homology did not depend on a triangulation. And then it was shown to be equal to the simplicial homology if the space were simplicial. And so you got it that way, and so then this wasn't pressing anymore for that reason. However, it still lingered as an interesting question. So what could we say here? Well, we can say just from this, now what we said is true if one of the manifolds has no three handles. That is, if it has a decomposition as a handle body with no three handles. Because then, and you should sort of see how this goes. You take the manifold that has no three handles and you put it on one side. Here it is. And then you've got a homeomorphism to the other three manifold. And now, this is a PL manifold, so, with second barycentric subdivisions, whatever, you divide it up into handles, the handle body. So there's 3 0 handles, 3 1s, and a 2 handle I've drawn here. And now, on the 0 handles, you wiggle them a little so they become straight, and they become PL. So you do a little isotopy, that's the K=0 case. And, well, I didn't say it, let me say it, I did say it last time in a different context, but remember that you can do this so that you just move things on a small ball at Rn, you make it PL there, you wiggle a little bit in the neighborhood of that small ball, and then you don't change anything outside. And that's kind of important because when I have to look at the 0 handle, I'm going to make it PL on a smaller one, on a smaller guy, and then, so it's going to become PL here. It's going to move a little bit around it, and then it's the same elsewhere. And then when I come to a 1 handle, I really want to attach it all the way in. Then it's already PL on the neighborhood of the boundary, and then you'd apply that, and now I make it PL, maybe it's something smaller yet, you're always subdividing. So now it's PL there. And you just keep iterating this process. And if you never run into a 3 handle, you just straighten all the handles and then it's a PL homomorphism. And so this is nice, and you can find PL manifolds with no 3 handles, especially if they're 4 connected, for example. But it's this theorem, well, if there wasn't the problem with the 3 handles, then we'd be all done. You just straighten all the handles and you're done. But now with the 3 handles, when you can't do it with them, then you'd like to somehow get a theory that doesn't have a statement like this, but says maybe there's no 4th cohomology, or maybe there's some other condition that's more easily checkable that you'd like to get. But anyway, you've done that. And then as far the other half, the Hopper-Looting is the uniqueness part. The other half is given a topological manifold, does there exist a PL structure? And it's hard to say very much about that, given this theorem, because in the topological manifold, you've got charts overlapping, and now you'd like to make the overlap be PL. But that overlap is bound to have 3 handles in it, or you're certainly likely to have 3 handles in it. And you don't know how to state any very good it's hard to get a clean theorem that says just when you can do that. So I can't even say very much so far with that. Okay, so a little bit more history. Straightening zero handles is the same thing as solving the annulus conjecture, and that's where that came from. Maybe, I mean, there's a little more history involved here. So just to bring that up, the annulus conjecture, historically, that's how I got into this problem. So the annulus conjecture said, suppose that in Sn, the blackboard, you have a n-1 sphere, and it's going to have a collar. It's locally flat, so it's going to have a collar, both sides. And then suppose you had another one that was disjoint, so I'll just draw the other one around. It's got a collar, of course. And so now this area in between is this, an annulus. In other words, is it Sn minus 1 cross I? Running across there. And again, this is sort of the same problem as whether an arbitrary homeomorphism is isotopic to the identity. You can't get your hands on. How do you get your hands on these two embeddings? So, actually the first theorem I ever proved was that suppose that somehow or other there was a patch here and a patch up here so that I could run a tube across. And so that it sort of fit down here. So suppose there's just a tube. What is that tube? It's an arc thickened up. And it fits together as nicely as you would wish at the other end. If you had such a tube, then you're done, because think about what the complement is. The complement, this annulus that we're wondering about, once you put a tube through it, this annulus is bounded by the rest of it is bounded by a sphere. It's kind of like I take a two-sphere, a smaller two-sphere, and then if I run a little tube between them that looks like this, the complement of that tube has bounded a sphere. That's just to connect some of this little sphere to this big sphere. So if you put that, that's a sphere. Well, then we proved the Schoenflies theorem. So the Schoenflies theorem says that what you see here is an end wall. And now you just have to glue it onto this thing, glue it onto this, and you get Sn minus 1 cross I. You're basically, you've got the complement is that, and then you just fill this in. And you can make that argument, it's not hard. So, as I said, this is the first thing I ever proved, and the first thing you ever prove is you remember. Anyway, so, but now what's the annulus? What does this do for you? Well, here's a little zero handle right here. That says I can isotope it and make it PL. So now this is PL. Now that's PL, and now this one's going to be PL. And now, of course, I can put this tube in there, because PL is pretty nice. It's linear locally. So I can put the tube through it, so it proves the annulus conjecture. It's not quite how I originally got there's a different train of thought, but that tells you how you get the annulus conjecture. Okay. So we've got 15 minutes. So the next steps are without, so you know, I've used wall here to do this when we don't have three handles, when k is not equal to 3. But if we didn't yet know about wall, there's still some interesting things we can do. There's still interesting things we can do because there's two theorems that I'd like to get to, and they have a bunch of nice corollaries. So one of the theorems is that so let me bring it back down again. So if this guy, or a finite cover, if this guy is concordant to the standard one, then we're going to be happy. So what's a concordance? A concordance just says it's not that this is PL homomorphic. It's not that. It's that manifold and the standard one have a concordance in between. So that means a PL structure on PK cross TN cross I, which is standard at one end and this at the other end. Well, that's asking for less than a PL homomorphism. But if you had that, that's enough. So we want to get a concordance, and concordance implies isotopy theorem. And then we want to get, the next step after that is to get what's called the product structure theorem, which is, so this has a sort of a history, this product structure theorem. So in the old days, there was a theorem called the Cairns Hirsch theorem, the Hirsch of Smale and Hirsch, which said that if a PL manifold MM given a PL manifold MM, if MM cross R has a smooth structure, then M has a sort of compatible smooth structure. So in other words, you can take a smooth structure on M cross R and bring it down to M. That was a nice theorem. That was hard work. Cairns probably did some version of this in the 40s and Hirsch in the late 50s. There's a Annals of Math Studies book in the early 70s where Hirsch and Barry Mazur wrote up a proof of this and done it the old-fashioned way. But the reason this is a good theorem is that often you could iterate this. So if you had something on M cross Rn, then you bring it down to Rn minus 1, then N minus 2, and all the way down to M. And it's often true that you can do something if you stabilize enough, if you cross with enough copies of R, you can often do something you couldn't before, and then this theorem brings it back down. So one application of this concordance implies isotopy theorem I was just mentioning a minute ago is that we'll prove a theorem like this, including top. It has all three categories done the same way. So for topological, PL, and smooth, any pair of those, if you have a structure on M cross R, you can bring it down to M. Assuming we avoid dimension 4. We always have to avoid dimension 4. I don't remember now whether they had to avoid dimension 4, but I suspect so. Yeah, actually, I know they do. So that's a nice theorem, and then just from that theorem we can get things like topological transversality, existence of handle bodies, various things, various applications. So all of that, all the stuff I just mentioned, is not going to use wall except for the case k equals 0. To get off the ground, you still have to have k equals 0.
With this theorem, you would get handle bodies.
Yes.
But
So you need to know.
Oh, for the topological version of this theorem.
Topological.
Ah.
Yes. And then you will get that.
Yes.
Yeah. So there's a number. So the way the next lectures are going to go is that we're going to put wall off for a bit, and we're going to make one assumption, which I'll explain. I'll explain it right now, I guess. So here's the definition. A homomorphism is stable if it is a composition. So homomorphism H is stable if it is a composition H equals H1, H2, H3, HK, finite composition. It's a composition of homomorphisms such that there exists U1 up to UK and HI restricted to UI equals the identity. So this is a homomorphism from the manifold to itself. So homomorphism is a manifold to itself. And it's stable if you can write it as this composition where each term in the composition is the identity on some open set. Arbitrarily small. Don't care. So that's a condition. It's actually a category, the stable category. You know, there's a subgroup of all the homomorphisms, let's say Rn, and then the stable ones are a subgroup of them. And you can talk about manifolds which are stable in the sense that their overlaps are overlaps by stable homomorphisms. So it's a nice. You don't hear about it too much. Partly you don't hear about it now because every manifold is stable. So you don't have to say so. And every manifold is stable because of this, the k equals 0 case of this. That you can take little zero handles, little disks, and isotope to the identity. Or isotope it to be PL, which is good enough. It's good enough. So, but before that, in the early 60s, Brown and Gluck wrote 3 papers in the Annals about stable homomorphisms and what you could do with them. And it was, before the torus trick, it was a nice category to think about. Well, so if you're dealing with a stable manifold, that's where the overlaps are by homomorphisms which are stable in this sense. If you're dealing with a stable manifold, then the k handle, the 0 case, is taken care of. And if that's taken care of, then you're going to see that we can do all these theorems, concordance applies isotopy, et cetera, et cetera. We can get everything without using wall. And there's some point to doing that, just because wall is a hard, long slog through a lot of topology to get there. Whereas, as you can tell, all this is pretty elementary. You don't have to know a lot to, you don't have to know much to understand that definition. Okay, well, I'm going to take a minute and just wave my hands quickly at the isotopic extension. So this will just get this out of the way. It won't be hanging over us. So the isotopy extension theorem. It's just a useful tool in various ways. So in the smooth case, we have f sub t mapping m into n into q into q, and it's an isotopy. Q belongs to sort of 1, and it's smooth. These are smooth embeddings. Embedding. A smooth arc of embeddings. That's what this isotopy is. And then the conclusion is that there exists a capital F sub t from Q to Q such that F sub t restricted to M equals little f sub t. So you can extend those embeddings to a motion of the whole ambient manifold. So that's the smooth one, and Milner, the proof, I always like this proof so much I can't not show it to you. So here's M, sorry, that's Q. You're getting a real low dimensional version of this. And here is F naught of M, point, and here's the time coordinate. That's the pi. So the manifold starts out embedded at time 0. And then what does it do? Well, it moves around in Q. But we're going to look at the, sort of the graph of it. So it moves around in Q. And it gets up here at the end. So there's the isotopy, just a picture of it. Well, we have a theory, smooth things have normal bundles, they have tubular neighborhoods, they have a nice, from the implicit function theorem and all that, you have nice neighborhoods. So there's really a nice neighborhood of this that gets carried along. So this is a tubular neighborhood, which is really M cross BQ minus M. So whatever this normal bundle was, it just gets carried along by the isotopy. That's sort of part of the basics of differential topology. Well now, because this is an isotopy, we have a vector field. So any point, there's a lot of drawing here are points, so any point has a path. And that path has a tangent vector field. Etc. And this vector field, I'll call this vector field V. So V sub t. Anyway, V at any point x has a component in the I direction of unit length, because of this thing, the isotopy moves along at constant speed along the time. So the component in this direction is always of length 1. Don't have notation for that, never mind. So it always does that. And it exists on this tube. Tubular neighborhood. Well, just take a partition of unity on this whole thing, Q cross I. Take a partition of unity where the two open sets are. One open set's the interior of this tube. The other open set is the complement of Ft of M. So two open sets. Open tubular neighborhood and complement of Ft of M. U1, U2. So pick a partition of unity. Well, first just pick the constant vector field partial with respect to t. Just a constant vector field everywhere in U1, U2, sorry. So U2 take that vector field, and U1 take this vector field. And now with the partition of unity, add them together. And the partition of unity on U2 is going to be 0 at U1. And the partition of unity on U1 is going to be 0 outside. And this can be a smooth partition of unity. So when you add them together, it just blends the vector fields. So you're going from this one to this one as you come across. So now you have a nice vector field. The partition of unity assures that you always have a component of length 1 in that direction, and now you just integrate the vector field, and that's the answer. So integrate the vector field, which is sort of EU1 of x times VB plus VU2 at a point x times partial with respect to t. These are the two partitions of unity. And you enter it in, you get the answer. So this is in Milner's notes from 1959 or 60. And it's just such a nice, simple, you can just see it happen. Nothing hard. Well, then the topological version is true. And I really say about one minute's worth of that. So now imagine the same picture, and because it's locally flat, so now this is a topological embedding, but it's got to be locally flat, so you don't hit wild things. So you've got the same neighborhood. And now we're going to use local contractibility. So if you look at a certain time t0, and if you take a short interval, which is not much different than, if you look at just a little open interval around t0, then not much has happened, which means that these different embeddings are pretty close to the one at time t0, close enough for local contractibility. So then, without touching f0 of m, or even a smaller neighbor of it, don't touch it, you're going to do stuff out here with handles or whatever, we know it from manifolds now, and you're going to use local contractibility to isotop back to what it was at t0, and then you're going to use that to sort of fix it at one part, but blend it in with the identity out here. So now you have to imagine using, this is all I'll tell you, use local contractibility in a thin neighborhood of this, where things are close to each other, and extend. So in other words, this is going to move a little bit, but this isn't going to move at all out here, and then there's going to be a blending in between. And so that means that you've extended it over an open interval, but this is a compact set, so you can do a finite number of those and you'll get the argument. So that's just a hint. That's kind of like a hint for your homework problem. Okay, 6 o'clock. Thank you again.